We are now going to go through a very brief overview of what is involved in developing a water balance. We can do this qualitatively, where we focus on what the key concepts are that can facilitate discussions with community members. Or we can also do this quantitatively, where we might want to draw upon the input and expertise of others to look at specifically how much water there might be in different parts of the water system. When we use simple models or tools, we need to keep in mind that there can be a high degree of uncertainty in these. Despite these, they have a number of advantages in that they can handle limited data and information, and they can be relatively easy to develop and to use. As we heard earlier, they can help us to understand the system, get a rough idea of what the key issues are, provide a framework for identifying what the key data and knowledge gaps are, and they can also be used to explore existing and future scenarios. We begin by looking at how we can understand the water catchment, and then within the catchment, how we can estimate how much water is available. We focus in this module on surface water availability. Whilst groundwater is much more complex to understand, it is also an important part of the water balance. The third part of a water balance is to understand what the water use or demand is. Whilst we don't cover it here, this allows us to compare water supply and availability with the need for water by both people and the environment. In the next section of the module, we will then talk about exploring existing and future risk. I will now hand over to Tony Nedelko from CSIRO in Canberra, who is a research technician who investigates the environmental interactions, resource use efficiency, and sustainability of natural and human-made ecosystems. Tony has contributed to the underlying analysis for our collaboration, including estimating catchment boundaries, along with land cover and soil type within these boundaries.
To estimate a water balance, we first need to understand what is happening in the catchment. A catchment is the area of land in which any rainfall collects and flows as runoff to the lowest point, in this case, the village of Satona. It is bounded by ridgelines, the highest points of the surrounding area. Runoff flows downhill to the valley floor, or it may form a stream or river if flows are large enough. A catchment is also called a watershed or drainage basin. The water balance of a catchment is the accounting of its rainfall input against its runoff, evapotranspiration, and infiltration outputs. To calculate a water balance, information about the catchment's properties is needed, such as its area, slope, land cover, and soils. Much of this can be estimated using freely available information and tools, such as Google Earth, topographic maps, or GIS software. Anything that changes the catchment's properties, for example land clearing, can affect the quality and quantity of water in the catchment.
This demonstration will show how to draw a catchment boundary using Google Earth. We'll begin by changing some settings in Tools, Options, 3D View, Exaggeration 3, and Navigation, Do Not Automatically Tilt. And we'll also turn on the terrain in the Layers panel. Our area of interest is Satona on Guadalcanal in the Solomon Islands. We can navigate through the landscape using our mouse to control the pan, tilt, zoom, and rotation, or use the controls in the upper right side of the screen. You'll see that where the mouse cursor is located, an elevation is shown at the bottom right of the screen. We'll begin by locating the top of the catchment. We can see that viewing the landscape, there's a valley that extends inland from Satona and surrounded on both sides by ridge lines, which will be the catchment boundary. Moving up the valley, you can see the elevations changing. We move inland, checking the elevations as we go. And eventually we reach a point where all the surrounding elevations are less. This is the top of our catchment. We can place a marker here. And save that. We can now begin drawing our catchment boundary. We'll open up a polygon, adjust the style and the color of the lines, and we'll make the area outlined only. We'll leave this box open and begin drawing a polygon. With the left mouse click, the first point is entered, and subsequent points are entered with additional mouse clicks, following the ridgeline down towards the ocean. We don't have to be exact because we'll be adjusting the points later. Moving all the way down to the ocean, we then follow the shoreline around the village, and then back up the ridge lines on the opposite side of the valley. If we click OK, our new polygon will be saved. We can now go about adjusting the points. We can reopen the polygon by right-clicking, Properties, and original points are shown. We can adjust points by selecting one and dragging it to a higher location along the ridge. Or we can also add additional points by selecting a point and then adding additional point further down and adjusting that one. We can correct the polygon in this manner all the way around its perimeter until we're happy with it. Clicking OK saves it again. The final version after all the adjustments is shown here. And we can see that the perimeter of the catchment follows the ridge lines around the valley. To see the details of the polygon, we can open up the properties again, and under measurements, we see that the area is 70.9 hectares.
In this activity, to understand the catchment, we would like you to think about what your water catchment looks like. Where is the catchment boundary likely to be? Can you visualize the ridge lines? What is the land cover? Is there forest, agriculture, grassland, bare soil, or buildings? Different types of land cover generate different amounts of runoff. How steep is the terrain? The slope affects the runoff speed, which can impact water quality from soil erosion. What is the soil like? Is it sandy or clayey? The soil type affects how quickly water infiltrates into the ground. What do you see when it rains? Is there a lot of water flowing down the ground surface? Do streams that were dry begin to flow? Is there flooding, or does water soak into the ground quickly?
The second step is estimating how much water is available in different parts of the catchment and how this changes over time. We can do this quantitatively using rainfall data and models to estimate how much rainfall becomes surface runoff or infiltrates into the ground. We can either use local observed data, such as what is shown here from 2 locations near Honiara in Solomon Islands, or by accessing regional data sets online, such as through the Pacific Climate Change Data Portal shown here. We can select on specific locations across the region, such as in Honiara, Solomon Islands, and we can get additional information such as annual rainfall and patterns between different years. We can also do this qualitatively as an activity with communities by asking questions such as how often does it rain, or how often does it flood, or how often is there insufficient water for drinking or household purposes. These types of questions and discussions can be facilitated by using things such as bar charts or graphs that show the amount of rainfall available, such as that showed in one of the earlier slides. But this isn't essential if the information isn't available. When discussing how much water there is, we can refer to objects that the community members are likely to be familiar with, such as the rainwater tank shown here. Once we have estimated the amount of water falling over the catchment, we can estimate how much water is lost from the catchment, and hence the amount of surface runoff and infiltration. When rain falls from the sky, it may fall onto trees, grass, or bare soil. Only a proportion of this rain reaches the ground to become surface water, or to soak into the ground and become groundwater. Plants such as trees may intercept the rain and stop it from reaching the ground. Plants may also use this water to grow, or the water may evaporate back to the sky. To explore losses with communities, questions can be asked such as, where is surface water lost in your catchment? Or how much water is likely to soak into the ground and become groundwater? We are now going to hear from Enif, who will give an example of a quantitative water balance. This involves estimating how much water there is in different parts of a catchment. Whilst the estimated amounts were made using observed data and a simple model, they demonstrate how the amount of water changes throughout the water system.
An example would be 0.6 megaliter rainfall drop over the entire catchment, which is equivalent to 60 large 10,000 liter rainwater tanks. Out of that, 20 rainwater tanks of water flowed off as runoff going down the slopes through the forest and may end up in creeks, rivers, and sea. And between 1 and 30 rainwater tanks is infiltrated into the soil and may end up deep in the ground, which can be found and used as source for water supply or stored underground as aquifers. The steeper the slope, with less vegetation, the higher the runoffs. The less steep, with more vegetation and forest, the bigger the infiltration, with the soil type in consideration. More runoffs can result in erosion or washing away the topsoil and chemicals from the land. This can also pollute water sources such as unprotected rivers, wells, and increase risk of flooding. For our work, what we use to make a comparison is on this is by using buckets. If you see on the slide, there's a picture of pot and a black bucket and blue and gray. Okay, we use this to explain the availability of water quantity. For example, if you see on the slide, we use this gray dish, the big one, and water is filled up to the top. It shows we give this as an example of a heavy rainfall. If that is filled up, and then using a smaller bucket filled with water, we show that as the runoff. And then a small pot filled up with water as what is being infiltrated into the soil. And that will explain the rainfall on a heavy rainfall on a steep slope with no vegetation. So yeah, so that people get a picture of what is when the rain when there's rainfall and there's a steep slope, which most of the water just runs off.